I'm going to talk about a new technology that we've released into the IBM JDK and into our OpenJ9 open source project. My name is Charlie Gracie. I'm the GC architect at IBM on our outreach collection stuff. Some information on how to get in touch with me.
So this is again GC quality of service issues.
Yep. I think this is going to become a pretty big theme today. I work for IBM, so don't trust me, don't believe me. Sorry, I'll skip. So for the talk today, I'm going to sort of go through, quickly cover some background and history of why we decided to develop this GC, the hardware support that we got implemented to make it possible, how the GC works itself, quick couple of slides on some results, and then sort of talk about issues and next steps where we kind of see the technology going as we move forward. So anybody who works on GCs or the Java VM at all probably gets asked these questions a million times. Everyone I talk to, customers everywhere, their major questions are and complaints are GCs are too long, they interfere with their application, what I can do to improve it. So for that though, the biggest problem is I always tell them that they can turn this knob between performance and shorter pause times. And for the most part, nobody wants to give up the performance. They don't want pause times, but they're not willing to eat any performance, is my experience. So how can we really improve GC pause times since nobody really wants to trade off a lot of perf? So the first big one is parallelism. All the GCs and every major VM has parallel collections, so I'm not going to talk too much about that. Concurrency is a big one. Probably 10 or 15 years ago, a lot of the global collections, everyone added in concurrent mark sweep. That really improved pause times for the average case, but it still wasn't great for performance, and you still had some fairly large pauses. So the next sort of big step in GCs for all the major VMs was to go with collecting a subset of the heap. And this subset could be a standard generational collector, or now in newer collections, it could be the sort of G1 and balance style collectors, which are doing targeted collections at different parts of the heap based on where they believe they're going to get a big ROI. So over the last 15 years or so that I've seen in GCs, the concurrent marking was added, opt-average pause. So I'm not sure if people are that familiar with OpenJ9, so I'll use the terminologies for our GC policies and what I believe is the equivalent for OpenJDK. If I'm wrong, please correct me. I'll update the slides. I'm not that as familiar with OpenJDK as I should be in Hotspot. Then the big one step for a lot of perf for a lot of people was moving to the generational collectors, which I believe I've already got an incorrect thing here for OpenJDK, to more generational copying collectors. In a lot of applications, people saw huge performance, even throughput improvements, and not just the GC pauses were better. They actually saw lots of improvements, mostly related to object locality at that point. So after that, we still noticed that there was the large global collection problem because you would do lots of generational collections, and then you'd have this huge outlier of a global pause. So pretty much at the same time, OpenJ9 started working on a balanced GC technology, and OpenJDK Hotspot was working on G1. And these collectors are region-based, and they'll still do their young generation collection, but they'll try and mix in other old regions as well into those collections, so they don't have to collect them all at one time in a global collection. You sort of include little bits and pieces of your old collection with your young generation collection. This would hopefully give you a more balanced GC pause times. So right as it stood before, or before a lot of these texts came out, like Shenandoah, our new one, ZGC, a lot of the GC pause times and most runtimes were always sub 5% for pretty much all logs I see. So the GCs themselves aren't taking that much away from the application time. but it's still sort of the outlier of time. Lots of new applications where you're seeing in the Java space are trading apps and in-memory databases and those types of things. And they really don't want, when they're starting to hit bigger heaps, a pause time of even 100 milliseconds. Yep, those should be 10 to 100 milliseconds and not seconds. I guess it is there. But in these collectors now, the sort of big thing is the dominated sort of responsiveness is really, in my opinion, on your generational or your copying collector. That is what most pauses are. People have been spending 15, 20 years tuning completely away from having global collections. So as much as possible, they tune away from them. They'll restart a VM before they get there, these types of things. So most of their responsiveness is solely based on the copying collectors, the average time there. So really, what's the idea? How are we going to improve the copying collector time? Well, it's actually going to be difficult. You could tweak some of the algorithms, try and improve parallelism, tweak things, but most of this technology is 10, 15 years old in these VMs and is pretty well optimized. Can spend a lot of time to get very small benefits, but I don't think it was going to actually come around to give us the huge wins that we were looking for. So we wanted to take some time and go see if we could actually do things concurrently, because we noticed when we were doing all our concurrent mark sweep, that was a huge reduction in our total pause times there. So if we could go and do something similar for our copying collectors, we would hopefully be able to give them the same type of wins. The really big drawback here is we were worried about large performance losses due to the read barriers. Anytime we wanted to do anything copying concurrently was going to introduce read barriers. So we were really worried about that. And we were also worried about copy storms. So at the start of one of these copying collectors, our idea was we were going to allow, if the application thread tries to reference something, it's going to have to then maybe go to the copy as well, or wait. In both of those cases, if this is a very common thing, we were really worried that that would actually eat up a large portion of the time. So you wouldn't have one stop the world collect that paused everybody for 20 millis, but individual threads themselves now may all be paused for 20 millis in approximately the same amount of time just to catch up with all this copy work. So how will we do this copying collector? We wanted to try and avoid the copy storm on application threads. I'll talk a bit more about that at the end. That's something that we haven't come up with a great solution for yet, but we also haven't seen it be a large problem. It's kind of surprising to us, but it's actually something that hasn't shown up and been noticeable. And I actually think it's reduced by some of the benefits of having the application threads themselves copy. And we went off and we started to introduce read barriers. So we just went through our code base. Because we support compressed oops, it was actually kind of easy to simulate a read barrier. We just went and changed a bunch of that code. But that really, just by basically doing nothing in the read barrier, other than just going and fetching the other address again, it was costing us about 10% of throughput. We figured then once we started actually doing real work, it's going to be even higher. For a lot of our customers, that sort of seems like a no-go. And it was going to force us to likely grow our objects to add another pointer or something, so we were also worried about the size of the heap. We then looked to see, could we do something to actually trap ourselves instead of that way we could just detect the reads. Operating system support in Linux and these things at this time was going to be really slow. That basically would have meant no performance. So we went off to some of the hardware teams and said, hey, is there something you can do on the hardware to actually give us the ability to do this in an efficient way? And hopefully in a way where we didn't have to do the pointer chasing. So as of the Z14 hardware release of IBM's 390 mainframe, I know you guys are all going to go home, try this out, because you have 3 or 4 of them sitting in your basement. It'll be great for everybody. It's actually like free heating for your house if you had one. In the newest release of the ZOS operating system itself and the Z Linux port. They both have support for making this guarded storage available. And it basically provides us with a very fast hardware read barrier. If you want to really bore yourself and try and read some text on it, there's a link here. There's a link at the end with all of the sort of different, I'm not sure I'd recommend reading it. So how does guarded storage work? A page with all those links. It basically provides you the ability to guard a region of memory. So you can set up, and it's almost able to handle all of the addressable memory space, basically because you can tell it what size each sub-region will be divided. That really restricts alignment for you. So if you wanted to start covering a terabyte of memory, your regions that you manage will be very large, and you will have not that many places you can start the memory off, because you have to have this alignment the alignment restrictions get very large. For this, they basically introduced a new instruction. So instead of a load instruction, there is a load with barrier instruction. That's mainly how we get to use this. The guarded load, basically, anytime you go to read a reference from a guarded region, it will go, and if the trap is enabled, it will jump to the trap handler. The benefit of this implementation is that if you go to the trap, it's basically only the cost of about 2 conditional jumps. 2 conditional jumps. That's not great, but you don't actually go there if you're not trapping. So the instruction and the claim from the hardware folks is that it's basically no cost if the trap's not hit. So in a lot of cases, it's not there. The one sort of gotcha with this is that when you want to enable it, you actually have to have it be enabled by each individual hardware thread itself. So I can't enable it for all threads. Those threads actually have to do it. So then that becomes part of sort of our barrier to entry, is that all threads have to at least come through this barrier before they can move on. So with this new barrier, we've introduced pauseless GC. I apologize a bit for the name. I was hoping to move towards no pauses completely, but we're really just, I didn't have the hyphen in the beginning. Now there's a hyphen, it's pausing less time, not pause less. You'll also notice it in a lot of places. The current place we're taking advantage of it is in our scavenger technology. So it's just concurrent scavenge will enable that, the command lines here. It started being available in IBM's JDK 8 SR5, and it's available in all of the source code that's in our Eclipse OpenJ9 project. We do have a software-only support for Linux x86. That's not enabled any of the IBM products, but if you pick up the Eclipse OpenJ9 builds, you can go run it with some not so great performance. So how does this really work? So the main thing we have to do is on JVM startup, you have to actually go initialize this facility. So that goes, you have to figure out how much you want to actually guard, divide up that memory. It puts a lot of work and trickery into our actual heap startup, because we have to go and now abide by all these extra alignments and query the OS for a bunch of information. But it's all there in startup. And then instead of waiting for allocation failures, of course, we can't wait for that. So the generational collectors are now kicked off at some percentage of when the allocate space is a percentage full. That's one of our heuristics that, well, I'll talk about a bit more later, where some problems can be introduced. And then we enable these read barriers for all object access. The great part about it just being a new instruction is the JIT on 390 now actually just generates this load instruction for all object access, because there's no cost if it's not there. So if it's available on the OS, it just uses it. So everywhere where we were doing our compressed OOPS barrier before, it was well known, so it was very easy for them to go plug this in. So they just generated the new instruction. And the interpreter relies on some simple checks just all the time to go and see if that barrier is enabled. So we had to now divide our generational collection into sort of 3 phases. So there are 2 stop the world phases. The first stop the world phase is pretty similar to a lot of the other low latency GCs you'll see. You stop, process the object roots. Then we set a bit that forces all threads on their way to go start executing to go set the barrier on themselves. And then we kick off a bunch of background helper threads. Similarly to some of the other technologies, we don't use that as many background threads as we would for parallel because we don't want to actually take over too much CPU away from the application. I believe it's usually about the number of cores divided by 4 or 8 with a minimum of 1. Then we basically allow the threads to go back and we kick off the concurrent phase. The background threads will continue processing exactly the same as if they were in one of the Stop the World collections. So it was quite easy. We didn't actually have to change very much of the code at all in there for this to be able to happen. And the application threads, so the big change for them is they'll actually have to jump into this read barrier for updating references if it's already been forwarded, or actually themselves to copy objects. And then we have another Stop the World at the end that basically we'll go through once we've made sure that there's no work left on our queue, and it'll process all of our clearable routes. And some of these clearable routes are now, in our first implementation, we're sort of treating as actual routes just to get by with a few of them, which we're hoping to remove in future releases. The benefit of our trapping read barrier is that we actually don't have to have any pointer chasing. Nobody will ever see an object that has been copied. They'll never see the old value for it. So that saved us on heap footprint, and it allowed that we didn't have any cost when you're not in the GC at all, or when you're not hitting an object that needs to be GC'd. And it also meant that we didn't have to change our write barrier at all. So that was actually a huge win for us on this technology. And another side benefit that we weren't really expecting to be much of a benefit, and it turns out that it is quite high, is that the application threads early on in this copy storm, it doesn't seem to overwhelm the system, but it actually means they start copying a lot of the objects in reference order. So instead of copying them in sort of allocation order, it's the order that they're referencing them in. And we actually see that that is giving the application some throughput improvements itself. In a few smaller benchmarks, which we run, they're actually faster with this technology than without, which I would never thought we'd see sort of peak throughput higher, but because of this, we believe we're actually seeing some cases where it's actually faster. So some quick charts on pictures of how it works. That's the old way. The new story that I just sort of talked through, they're here for people if they want to look at them afterwards in the slides. So the guarded storage interrupt handler, on startup, you just have to register. There's an API that you go register what you want to happen when the trap happens. So I just wanted to throw up quickly sort of what the trap looks like for us. The first thing in the red is, so this is going to be sort of macro assembly generated code. We have some macros that basically will save all of our working registers. We then go down and load the pointer to our C callable read barrier, and then call it, then come back and load everything back and switch to Java. This right now is not highly optimized because we're going to go make a C call here, come back. We're saving every possible register. But this allows us to share the code completely with our interpreter barrier. And since this is only happening in the slow path where you actually are going to have to update something, we haven't noticed it be a huge loss. But in the theory, we could go and reduce this down and inline some of the more faster paths, in particular updating the reference if it's already been copied. So what the barrier looks like itself, pretty similar what everyone would expect. I think Alexei showed something pretty similar. check to see if your object is in your evacuate space. If it is, got to check to see if it's forwarded. If it's forwarded, you're just going to update the reference that you had from before. But if it wasn't, the application thread or whoever's going through the barrier will actually go do the copy. Once you have the copy, the one case, the special case, is if you actually run out of memory. So we will copy in our VM. We have an allocate in a survivor space. It's a little bit different than some of the hotspot VMs, but we could possibly not be able to fit everything we need to copy into survivor space. In that case, we actually just self-forward the object, and we'll fall back at the end to a global collection then, which will go and do a full global collect. It's not a great story right now, and that's one of the things we hope to improve in the future. But this self-forwarding just is something that the global collector can then recognize and fix up as it's doing it, the full collect. And then at that point, we'll go off and compare and exchange in the new forwarded object to the address. So some sort of quick results here. On SpecJBB 2015, the reason we use this one is SpecJBB 2015, for people who haven't seen it, it has sort of a max throughput that you can get, but then it also measures what it calls a critical JOPS, which is really dependent on pause times because it has to make some sort of service guarantees on how quick the transactions can happen. So this is actually sort of a good example for these type of GCs. So on the left is our default collector. The blue lines are the max JOPS and the orange is the critical JOPS. You can see that we lost about 3.5% on the max JOPS, but we more than around doubled the critical JOPS. So that was actually pretty huge for us. It's about what we were hoping for. The max JOPS was actually a little bit better. My goal was to not be worse than 5 to 10% on most things. So the fact on this one we were here at about 3.5 was pretty good. This chart is sort of showing the GC pauses for both of those runs. They're both in red, I apologize. The top line is from the default collector and the bottom line is with concurrent scavenger enabled. So with the default collector, it was averaging about 30 milliseconds per pause, and we were down to 3 milliseconds was the average pause with this collector. So most of the time you're seeing about a 10x pause time on this workload. When you start to get into really big GCs, since this isn't really dependent on heap size, it's more dependent on root set, the pause times tend to sort of be down in this no matter how big they were in the other collections. So we ended up with a bunch of things we had to sort of work around or some known issues in our technology right now. So that's sort of the big things we want to look at more as we go forward in the future and keep running this on some more workloads. There was a lot of things, internal VM caches that we turned off because we didn't have proper barrier support for them built all around the VM. And some of the cases, it was actually going to be quite costly to update them for the wins that they were. The biggest sort of one was our monitor caches for when we don't actually have monitors for objects. They go off and hit a hash table to look them up. So we cache a bunch of the most recent ones. So we had to turn that off because it was something that was going to be really slow to update. Our kickoff heuristic is one of the things that we end up having to tune with people when they're using it the most. And it's because we're sort of aggressive on how long we could go and on some technology decisions we made in the past. So I mentioned before that we divide our space into allocate and survivor. It's by default 50-50, but you don't want to waste all of that survivor space because the whole generational hypothesis is not that many objects survive. So we slowly tilt the allocate space to be more of new space all the way up to 90%. That means when we get things wrong here, now our guess is wrong, we have a lot more area for failures. And sort of the biggest sort of pain that we're seeing right now is on really large objects. So when an application thread hits a large reference array or even a large primitive array and it has to go copy 8 megabytes, 64 megabytes of data, that's all happening on this one application thread. It can start to see some noticeable pause times. It's not in the order most of the time of tens of milliseconds and things like that, but it can start being a millisecond or two in some cases for really large arrays. So we targeted our scavenge because that was what we believe would be the sort of biggest bang for a buck, biggest proof point to start off with. So we still have a lot of work to do with that one. Like I mentioned, we want to fix all the cache work that we had to turn off. We actually believe we can remove most of the stop the world pause time completely. The starting one, we think we could actually come down to just sort of be sort of a quick barrier. All threads sort of have to check in, but once they've all checked in, we can just go. We think we can get rid of the rest of it, and it could happen completely concurrently. And the end one, we think we can basically get rid of, but the small cost for that one, we're not sure is worth the engineering effort at this point that we would put in to get rid of it. So it's still something we're looking into, but we're not sure what we'll do with the end one. And we want to introduce, and actually very recently, it has, you'll see a bunch of the code went in if you look at the project, to actually be able to copy, share, and wait for the large objects. So because we have the background threads working anyway on the side, if an application thread starts to copy one of these really large objects, it will actually just do a small piece of it, put the rest, set off the rest to be done, and then wait until it's completed. So that gives us, hopefully, we're starting to see some decent benefit on those if your concurrent threads pick it up quick enough. But when you start talking hundreds of microseconds, we're not sure that that one's really going to pay off either before they'll get there in time. So still an investigation we're trying and looking into, but we'll see how that one plays out. We want to then move on to do our compaction for the global collection the same way. We believe we probably won't be able to interleave them. So if we started doing a global compaction, because of the way we have to divide up these memory regions and there's only 64, we may not actually be able to be completing a concurrent compaction while we still actually would then go do a nursery collection. So we'd have to abort the global compaction at that point and just do the scavenge. So it won't possibly be as effective as it could be, but it would be an improvement, hopefully, in the pause times if you need to compact. We also want to move it to our balanced region-based collector, but the limit of 64 regions right now really limits that. By default, we try and have between 1,000 and 2,000 regions in our balanced collector so that we can share work and things work efficiently. If we have to limit that down to 64, the pause times then become quite big in the stop the world parts there, and it's not as efficient. So we're going to talk to the hardware guys again. We're hoping that we prove this technology is useful and we can convince them to make more additions to the hardware, but we'll see how that goes in the end. More platforms. I assume nobody here has a Z14 machine, so the newest version of the open power spec included very similar technology. No one has fabbed it in chips yet, but it's there for anybody who's fabbing PowerPC chips. Again, probably not everybody here. Looking at the roadmap for x86, there might be some things we can take advantage of from Intel, and also want to see what they're introducing in the future, and to also see if we can improve our software read barrier and have it more similar to how some of the other technologies are working so that we could have that as a viable option as well. Now that we know all the places we have to change, we could probably do it with some extra modifications around our write barrier and stuff to be able to use them. So sort of a quick conclusion here. This is here on Z14. we were pleasantly surprised by the performance loss. We haven't seen anything at the 4 or 5% or higher yet, what we've measured, so we're pretty excited about that. The pause times of around 10x and things, reduction is pretty awesome. We're pretty excited and pretty happy with that benefit. And the unexpected benefit of the object locality was really a good one for us because we think it actually is outweighing the copy storm. But even tracking some numbers in debug builds, we're not even seeing the copy storm as something that hits that much. We're seeing, I wish I had the numbers now, but it's about 10% maybe from the last run I was looking at of objects copied by the 10 to 15% by the allocation threads themselves. It seems that they're copying the important ones on their path or something. So that's why we're getting the win and not seeing huge losses. So I'm open up for questions. It was sort of a quick overview. I was kind of hoping everyone here is a VM techie. I wanted to leave time for questions so that people had time, they can ask lots of questions. Like I promised, there's the link slide and things. And I'm here. You can look at most of the code in the Eclipse OpenJ9 repository, and I'll open it for questions. All right.
You mentioned the slow path. You take an interrupt. It's the cost is similar to a couple of branches.
Mm-hmm.
Is that an OS ring change, or is it a sort of a user mode interrupt where you vector in user mode?
I believe it's an OS ring change. Yeah, because we end up registering the code we want to execute through some API in the beginning that I believe it ends up running. I'd have to ask the guys a more detailed question, but I believe it ends up running sort of in OS side of the world until you then jump back out.
So I assumed it was a user space thing as well. So in that case, how unreasonable would it be to do page table trickery in x86 land to get something similar?
I think we could do that. That's one of the things we would like to look into for x86. I believe it's been tried and done before, so it shouldn't be too crazy.
My worry would be, right now we're in this atmosphere where telling the kernel to run some code for you is not a politically correct thing. For good reason.
Yeah.
So I think that whole inject some code to run on a chop is unlikely to go well in the x86 land.
Hypothetically, if you got it past legal, the notion of using critical JOPS as a benchmark is kind of an interesting way of thinking about performance. Do you have any sense of, like max JOPS obviously would be great. Do you have any intuition for how critical JOPS would fare if you did the naive thing?
The critical J, some of the initial stuff, or when we're running right now on the x86 version, we see similar improvements in critical JOPS, but max JOPS is so low. It's really, it looks similar, but I'm not sure I believe the numbers. It actually looks a bit close, like even closer, like the critical JOPS is even higher than on this one, which that's why I'm not sure. I think everything is just so slow at that point that it's really not a great measurement at all. All right.
So weak reference processing, things like that, and class unloading, do you do that concurrently as well?
Our generation, the scavenge never did class unloading, so we only rely on that for global collections. But we do process weak references, and they'll be processed as part. They happen in the stop the world phase.
What in particular is it that is so hard to emulate about this instruction from a sort of common sort of instruction set perspective? I mean, except for essentially comparing something global and just jumping out sort of to a alternate path. I mean, from your perspective.
Oh yeah, sorry. So the question is, why is it difficult to emulate this instruction in software? I don't think it's particularly difficult to emulate it. The difference is you end up living with the check all of the time, even when you're outside of the GC, so it's always the perf hit.
Yeah, but I mean, on x86,
Yeah.
The load is speculated and the compare is speculated, so shouldn't be that.
Well, yes.
Which is
Shouldn't is the right.
I mean, if you don't do link changes, you're all fine still, right?
Yeah, and it probably is something that would be doable and start making the performance of our software one be a lot better if we just start emulating it that way. The difference is the more we emulate in that direction, but it still forces us to then, we have to make further modifications for any of these things, because then you can't guarantee that people have only ever seen it to begin with. So I believe we'd have to go and then start modifying our write barriers and stuff, so, which is all fine as long as the perf is much better. It's not that big of a deal, but we're trying to keep both sort of similar right now. So a lot of the other software solution is actually right now, the reason it's really terrible is we're actually using, we're just page protecting the actual pages and letting it jump through the OS. Like, so very, very slow. Just to keep the two implementations basically identical. But if we want software, we're going to have to go the route of emulating more of it that way with the instructions. All right, if that's it for questions, I'll stop now and let everyone get a couple extra